Right, welcome to our second part of data handling. And what we are going to do today is follow up on the topic that we did 2 weeks ago or in the previous lesson. What we did was we had pandas, the pandas library, and import functions from that library in order to import data into our kernel, into our Python environment, in that case, a JupyterLab notebook, and then looking at certain features of the data and also using simple plot functionality to get plots. So we build on that today, and we have two parts, and actually very important part, key concepts that you should really look into it, even though I'm sort of making things simple and it doesn't feel like it's very special, maybe if you just look at the examples that we do today, but it's very profound in terms of understanding what goes on in machine learning. So yeah, let's start. Let's try to remember what we did from pandas. Is my screen sharing? Okay, so we started by importing the function that we need, and that was read CSV. Read, is that big enough? So I'll make it slightly bigger so you can read it better. Maybe that's better. And among the many options that pandas offers, just use read CSV with the sub in between. So that function is now there, and another that we will definitely use, want to make plots now that we know how to do plotting from matplotlib.pyplot. Quite right, .pyplot, import sub, and it's subplots with the plural S that we're going to need. So I import those functions, and we're then going to use it in order to read data into a data frame. Now, before we do that, just a small comment, because you will find it so often. If you look up anything regarding functionality in pandas and you find a tutorial where somebody shows you how to do it, similar to what I'm doing here, people will do something like import pandas as PD as a first step. And then later, when they use, for example, this read CSV, they will use PD, short for pandas, dot, and then say read CSV, and then put the parentheses. So this way you will very often see in demonstrations. We recommend that you don't do that. So do what I show above, import the function that you need, even if that's in a long script, 20 or 30 functions, just put them there. It's not much to do. It's you just copy and paste it if you go to a new script anyway. And the reason we don't recommend this because importing pandas just imports the whole library with just everything there is. And if you do the same thing importing NumPy, that can be on the order of 100 megabytes or so, which is then in your workspace, takes up a lot of memory and just no use because 99.9% you will never actually use. And so don't do this. You can, of course, you can do it. It will still work, but to save memory and to keep things clean, just you can import the functions as you need them. Oh, by the way, if you don't know this notation here, you can, of course, just use import pandas by itself. But in that case, you would actually have to spell pandas here. And if you use an abbreviation like as PD, I think that's what most people use, then you can refer to it as PD for pandas library, just for short. And so, of course, if you have code there that you copy, it will always say PD dot whatever it is. But it also means you know where the function comes from which library. So it's easy to adjust the code later on. Okay, let's just delete this. And let's now read our data. So our data frame is supposed to be read CSV, and then we do it from where my data set is in a folder called data. So I call it data, and I have a couple of files there. These are the ones that you also have for download for this lesson. So I'll take the patient's data set, just a very small data frame with a couple of columns. And of course, if we want to see, maybe you remember, add is the function to use to show what we have got once the data are imported. So I refer to the name of the file in quotes. I give the path with the subfolder, and then the whole name and df head shows me the first 5 lines of that data frame. So it's not too many columns, couple of columns, and first 5 rows by default. So first thing you might ask is how many rows are there? And maybe you remember df shape tells you there are 100 rows, 7 columns. A couple of observations to notice. So the data that we use, of course, exclude the indices on the left-hand side. They are just for orientation. And of course, they exclude the titles. So they are just names to be referred to, like a dictionary, if you remember keys in a dictionary, or just titles to have a handle to go to that column if you want. You notice there are different types of data. So specifically, you see some numbers, and on the right-hand side, so you see some letters. So the letters would come as a string, male, female in this case. This is, of course, different from the numbers. And even among the numbers, you have 2 types. You have 1, 0 here, which is binary, which you could also interpret as true, false. Then you have integers. The first 2 columns seem to be integers. There's no dot, nothing. And then you have floating point numbers in columns 0, 1, index 2, 3, 4. So that we have to keep that in mind, because it will become important when handling. If you want a function to be applied to the whole data frame, it might complain about things. If you want to divide everything by number 3, then of course string will not be easy to divide by 3 unless you make specific preparations for that. Right, so let's remember, how do we do a plot? So that was, and describe, right, to get mean and median and minimum, maximum value and standard deviation and so on. Another thing that you might remember, how to do a plot now of a data column, fig, ax. So that's my sort of standard abbreviation. Create a figure. Within that figure, put a coordinate system and use subplots to generate that. And then on the axis, say what you want to have plotted. So let's just say plot. And then how do we refer to one of the columns? We use data frame df. And then we can give a name in quotes. For example, age. If you remember, one of the columns was called age. And if you want that age plotted, there you go. Maybe you remember the semicolon to suppress this unnecessary line of comment, which we are not using here. And so you can do those things. There's also ways to then specify, I don't know, is it to specify that you want to have markers and different types of line and different colors. Let's do one color, C, keyword argument C. And then if you want the whole thing in red, then you just specify R or red as the way you like it. C equal is the keyword argument, what color to use in the plot. Right, so this is, if you remember what we discussed last time, this is something that refers to one column only. And as such, anything that you conclude from seeing this graph is univariate. Whether you call it analysis or no, it's a univariate view of the data column by column. So let's try, just copy that code here. And let's now try and see a bivariate feature, meaning we are now going into multivariate data features, or features that include looking at relationship between columns, not just the column in isolation, but relationship between colors. So what can we do? So the first thing that we can do is the scatter plot. It's the easiest and probably the most widely used feature to look at the multivariate feature. It's bivariate because we have two columns that we look at the same time. And scatter plot then requires the specification of two columns. So first the X, which goes on the horizontal axis, and then the Y, which goes on the vertical axis. So let's define in the data frame. So say we have, what do we have? Let's say height and weight. Height, so that's the one column, and then comma, and then define weight. So see height horizontally against weight vertically, and there we go. Forgot to put that semicolon at the end, so no annoying text here. And that's what we have. So of course, you can then experiment and plot whatever you want against whatever you want. So remember, there's something called age, and then looks like this. And what else do we have? Smoker. Let's try just for fun. Say, what is smoker doing? Well, smoker is binary 0 or 1. So this is what you get when you plot the age against the smoker. So maybe not everything very meaningful in this case, because smoker is binary. It's just a yes or no thing. It's not very good for making such a plot because it's no quantitative differentiation. It's a categorization. It's a categorical variable. So let's go back to our height and weight. And we have sort of a certain distribution, a couple of points scattered around here. If you want to remember, I think maybe it's a good thing at this point to start introducing some more features of matplotlib. Set X label. You can specify what is on the axis. So in this case, it's particularly important. X label is height, and I just copy and paste and put the Y label, obviously put weight, because then when we see the figure, we can also see what it is that is displayed on one or the other axis in case we forget. Right, so another experiment that we can do is, well, before we go that, what do we see here? So we see scattered dots where each dot is defined by two coordinates, one on the X and one on the Y axis, right? It's like a coordinate system. You have two features, as we will call them later, and both are quantified. And so you have every point is defined by a pair of coordinates. So the first point, if we just go up to the feature, the first point, 176 in weight, and where's the height? Oh, height 71 and weight 176. So the first point is, if I scroll down, 71 and 176, somewhere here. All right, so that's basically how to interpret this thing. And then what do we learn from that graph? Well, mentally, what we do is we compare it to a null hypothesis. Now, what would be the null hypothesis here? Well, if we are looking for relationships between data, then one possible null hypothesis is that the data have no relationships between them, right? If there's no relationship, then this is a standard assumption. You measure one thing, you measure another thing. Maybe the two are independent of each other. And that's the null hypothesis that you can formulate. Now, if you have that null hypothesis, what would you expect it to be? Of course, you can answer this question, what do you expect it to be in code? You can do all the coding and we'll learn all the functions that are needed for this. But now just verbally, what you would expect it to be is that you have the certain heights on the horizontal axis, and they're distributed because some people are higher, some people are shorter, and some are in the middle, and they will have a certain distribution. And then the same goes for the weight. And if these two are independent, then they will just be blurred around with no apparent structure in the way these points are scattered. So in structure or a relationship between the data would then mean a deviation from that sort of diffuse scatter that we expect for independent variables, and some deviation. And one of them you can maybe already see a little bit or sense a little bit. And that is in this graph here, as it's done by default for Matplotlib, the upper left corner is fairly empty, whereas the upper right corner here is more densely populated by points. So that tends to sort of that tends to suggest that there might be higher values in height. Taller people might be heavier. And this is confirmed by the fact that lower left side seems to be a little bit more densely populated than lower right side. So if that was actually the case, then there would be a trend for the larger the person, the higher the weight. So that would constitute a correlation if there was such a relationship. And of course, you then might think, yeah, well, maybe I tried to fit a straight line to sort of express this kind of trend, a regression curve, as you probably have done already. So a specific feature of those scatter plots is if you plot a variable against itself, so height against height, that gives you everything on a straight line. And you see it looks like very few points. We'll come to that in a second. Or if conversely you put weight against weight, then more densely, but then the same on a straight line. This is trivial because one variable against each other, points are identical, so they must be on the main diagonal. And densely populated, we'll come to that later. Another thing that's important is to have a look at what if one variable is exactly the same as the other, but multiplied with -1, so negatively taken. So I put in a minus sign before that, so weight, and I plot weight versus minus weight, and that's a falling graph, so decaying or negative slope, if you like, if you put a line mentally through that, or if you regress with a linear function. And that would be sort of the opposite trend, right? The larger the height, the smaller the weight. Not that we would expect it to be, but of course, two variables can have that relationship as well. Let's go to our original. It was the plus relationship. So an increase, meaning that there's a positive correlation. When one goes up, the other goes up. And we assume that something like this, to some extent, this might be the case even in this curve as well. So how would we express this kind of trend, or this idea of having the larger one is the larger the other gets? Well, I mentioned it already. Regression with a line is sort of what we can do mentally. We can sort of think, what if a line went through them? We can, of course, also plot the line. So let's do that. Let's use that same graph and plot a line. So add a line before we put the labels. So how do we do that? Now, plotting a line is a very useful feature to know. We use plot. There are other possibilities, but let's try to use plot for a certain reason that you will immediately understand. So how do we do that? We can plot a line if we specify the x coordinates, comma, and the y coordinates. So we can do that. We can specify the x coordinates. And the way we do it is we go from 0 to 1. I'll show you in a second why that is. And then we do, as a second argument, the vertical or y coordinates. And we do the same. We do from 0 to 1. So that would be a diagonal. Yes, a diagonal. So if, increasing line, but it starts from the origin, 0, 0, goes to point 1, 1, x and y coordinates, 0, 0 to 1, 1. And of course, it will not fit in that graph, right? Because this graph goes from 60 to 72, not including 0 and 1, and 120 to 200 on the vertical axis, and the same not going from 0 to 1. But there's a trick. So if I go back to the line where I'm just coding currently, comma, there is a keyword argument. Sometimes you think there's a keyword argument for everything. In this case, there is. And what we do is we can use transform. That means we can transform that piece of line that we have. Now it's 0, 0 to 1, 1. We can transform it such that it fits in our plot. Okay, and we can do that by saying in the axis system that we have, and the argument to give is transaxis. Axis. So it's trans and then camel, uppercase A, X, E, S, transaxis. And if we do that, we get the diagonal line. If you remember that way that we did before the color, maybe we do it in red, so you can see it better. I would just like to show you the code such that if you code with me so you can see it at the same time. So that's how we plot the line, and you can see the result. Very wonderful. I mean, wonderful in the sense that the line actually goes from the lower left to the upper right corner in the plot that we have, whatever the plot is. So it's a very generic way, so remember it when you need it. So what do we see? That line would sort of indicate if it was along the diagonal, then this is what we would expect, the red line, and sort of if points scatter around that red line with a tendency to follow it, then we might suspect a positive correlation between the two variables, which is not so unplausible. People who tend to be larger can weigh more and thus be heavier. So it's a reasonable thing. And we'll see in the second part how to quantify those things. So that's our main result. Use the scatter plot to see the relationship between any two variables. And let's just try another one for fun. What else do we have? We have the systolic or diastolic blood pressure. Let's just put in one systolic blood pressure, and then we have to adjust the Y label because it's now no longer the weight. And you can see if you plot the systolic blood pressure against the height and plot that same line, there isn't any particular tendency that we could see. I mean, the line just cuts through it, and it's just fairly irrelevant. Means we see a scattering of the points, but not necessarily a relationship that tells us there's a positive correlation between the two. And now in this plot, you can actually see very nicely what I meant before. The height is sort of aligned. It seems that it goes aligned along lines. Can you see that? How these points seem to be along lines, which is of course a fact, a consequence of the fact that in the original data set, the height was given in integers. Right? So if we go back to our plot, so 64 is aligned, 65 is aligned, 66 is aligned. Not what you would measure if you would precisely measure from the ground to the top here, but it's done in integers, so that's why you see them sort of strangely aligned. If you see something like in other data sets that we provide, if you see such a thing, immediately go and check why such a strange alignment is there. If there are rational numbers, it shouldn't be there. If it's there, it's for a reason. And in this case, well, we don't mind whether it's 66 or 67 kilos at kilogram. So they're also all very light, not very heavy people. Okay. And then you can see that there is a reason for this, which is outside of the plot, which is a numerical way of presenting the data, of course. Okay. Let's do another experiment. Let's do copy and paste that code. Go back to our weight, because I like that. Let's repeat. So we have our thing plotted, and let's look at another keyword argument, another feature of Matplotlib to do plots. Of course, everything that you can manipulate here, you can play with, and you can check how it changes the visual impression. Can you see that? Maybe it's, I don't know if I leave it here, or maybe I take it away. We'll remember, right? You have seen it so often now, you will remember. What I wanted to show you is a keyword argument called S. And S is short for size. And size means the size of the round thing, the round marker, that circle, that filled circle, which is plotted for every point. And if you don't know what it is, just try a number, just try 1. And the result is such that the dots are so small that we can hardly see them. Right? So what we can do is we can modify things, and we can make it 10. And getting a little bit larger, making S 100. And then they're getting similar to what we had before. 1,000, even larger, 10,000, very, very large. So the important thing is here, of course, the visual impression, as you have just witnessed, changes depending on what marker size I use, right? So the value that is there by default, nobody knows, comes from somewhere where if we modify it, we can see it makes a big difference. So this is something to keep in mind. As much as possible, remember to check those default values, because you might improve the visual impression by adjusting things correctly. Specifically, what we see now is this kind of, what do we call that, sea or ocean or something, which is just plain blue for most of the area that we are showing here. And so it doesn't show us any structure, just, well, they are so big, they all overlap, right? And if you remember when they were 1, they were all isolated, or like these little pieces of dirt that look there on the screen. But something more interesting is somewhere in the middle. If I go back to that value 1,000, for example, look at this plot here. So what you see here is different. Now, in this case, we have, I don't know if I use that water image because it's blue, that could be something like 2 lakes. And you see like there's an upper lake here and a lower lake here, and then maybe a puddle here. But that's, of course, interpreting visually that they are fusing, right, or overlapping. So and what I see here is this kind of upper lake, lower lake, means this suggests that there's a certain structure in those data, in the points that have been provided, which with a certain blurriness or size of the circles can be viewed as possibly belonging to 2 lakes or 2 groups or 2 different categories. And this is, of course, something that is equally important, because if you remember before, I said correlation means, yeah, if one variable goes up and the other also goes up, so they are correlated doing the same thing. Another relationship that we might find in a scatter plot is that they go into different lakes or different bubbles or different groups. So if that was the case, then of course an independence of the 2 data is no longer guaranteed, but it means, or one could interpret, they come from different distributions, right? So especially in this way that I have it here. Why? If you follow my mouse cursor, if you can see that, you can just try to find like a ship in the Suez Canal. Can try to navigate the mouse in between. It's a bit narrow here, but I still get out, and yes, there we are. So you can actually make a separating line between those two groups of data that I have visually now discerned based on the kind of size, bubble size that I use for the plotting. So let's now try to do that a little bit more quantitative in the sense. So what is it that actually distinguishes those groups? So what we can do is we can use the tool that we have already learned, and we can use our line plot. So we know how to draw a line. So let's use it. Let's put a line in here on that axis. Just use the same piece of code. That's all fine. And then what we see is that straight line, of course, is the diagonal. And well, it doesn't really tell us anything any more than before. Maybe there's a tendency for larger heights to be associated with larger weights. But we can do something different. If you look at this gap between the two data, between the two lakes, this white gap here in between, that might be somehow adjustable with a line. Let's just try to adjust the line such that it fits in the white gap. So what would we do? First of all, we suppress the output, putting this here. And a line that goes from the left upper to the right lower corner would, of course, just be the inverse of the one that we have here. Namely, instead of going from 0 to 1 in y, going from 1 to 0. Right? So this is our line now that goes from top to bottoms. The anti-diagonal, if you want, is sort of the line with negative slope. Same as before, slope is now -1. And that's not so bad, right? Can you see how all of the points of the upper lake, so to speak, are above the line, and many of the points of the lower group or lower lake are below that line. So meaning if we adjusted the line a little bit, we could actually maybe separate them much better. And I'm not going to go into more things, but you can like guess if that lower point was a little bit higher up and the line went something like to here, then it might be better separating. So let's just try something 0.3. Oh, that was the wrong axis. I don't want to change the x coordinate. I want to change the y coordinate. So 0.2, yeah, better, not quite. I don't know, 0.5, even better. So I can say they're almost perfectly separated. Maybe 0.24 is good. So you can see we can adjust that line such that it separates the two visually discerned groups. And now we can see we have this bubble up here, all the data points that are one group. And we have the rest down here with that one point falling out in the other group. And of course, having that line, knowing the equation for the line, and it's basically written here. We can put that into a linear equation directly. We have an equation to separate those 2 points. Why would that be of any importance? Well, if the next patient comes to the practice and the assistant there takes the height and the weight and puts them into the system, then we get the new patient's recording. We can immediately predict whether it falls in the group above the line or in the group below the line. Whatever that means then, I think this is artificial data, so it doesn't really mean much, but this is how we can then distinguish. We can predict based on this model. The model is the red line, separating the 2 groups, and any new data point can be used to predict new incoming data as with respect to this line. So if you think, why is the guy talking so much about a couple of distributed points? What we have now done the last 5 minutes was essentially manually doing machine learning, right? That's it. That's how machine learning works. It looks at multivariate features, in this case exemplified very simply by features between 2 variables, and it tries to find whether there is such a thing. Is there a way to separate them into different groups? because if it's one thing that you measure and they are independent of each other, they wouldn't fall into two groups. They might just be nicely scattered diffusively, like we saw before with that example with the systolic blood pressure. If there's such a thing like a gap in between, there are ways to find out about this and to fit some mathematical function between those two, like this red line here, and then use a categorization based on that line. So that would be like the model, the red line, and training is adjusting this one coordinate from 0 to 0.25 and going back to 0.23. This is what happens in the optimization step in machine learning. And then the outcome here, say that equation with that slope as it can be calculated from this equation, that would be then the fitted model which you use to predict whether your new patient is above in the group above the line or in the group below the line. Okay, so I just wanted to show how a little bit of experimentation using the marker size and putting in a line, how that already shows you what the machine learning in fact does when you give it data and use some complicated algorithm. Now that we have done it sort of manually, verbally, qualitatively, we can now see how all this can work more quantitatively. And the only thing that we're going to use is we look at the correlation coefficient or the correlation matrix as one way of quantifying a whole data frame's presence or absence of relationships between columns. And so it's an important overview that you should always have before you start looking into your data set, because it already allows you to conclude a lot of things about what algorithm to use and how possibly to make things simpler and so on. Okay, so let's start with the same thing as before. Of course, we need the data. Pandas import what? Read CSV from matplotlib.pyplot import subplots. Anything else? No, we don't need. Our data frame is read CSV of something in the data folder, which was called patients. Just use the same data set for simplicity. And the head. Okay, so if we do it, we have our data here and it's the same as before. So no surprise here. You remember how to do describe and get the mean, the median, minimal, maximal value, standard deviation for each of the columns and so on. So we don't do that again. Now, when it comes to calculating correlations, of course, that's a whole field in itself, but just very quickly, how do we calculate correlation? Well, the quick fix, so to speak, is using pandas features. So pandas is very good in giving you functionality to just get what you want right away. Maybe a little bit similar to MATLAB. So in a sort of object-oriented paradigm, you would use the functional method cor, which is the correlation. And if you apply it to the data frame with the open close parentheses, you remember no arguments given, use all the defaults, we get as a result the correlation coefficients for every pair possible with that data frame. Well, every pair, let's go back and see how many columns do we have? 1, 2, in the frame 1, 2, 3, 4, 5, 6, 7. In the correlation matrix, you have 1, 2, 3, 4, 5, 6. And you can guess immediately the reason, because to calculate a product between a number and a string is not straightforward. And so the string column has been omitted just by default. If you want to include it, you can try it, but it will throw an error and then you have to do something to convert female into numbers that you can use for calculation. So it's quite convenient. You just say core and then you get the correlation in form of the correlation matrix. Okay, quick summary. I hope that you know it. If not, look it up. Go to Wikipedia or somewhere, find correlation coefficient. Pearson correlation coefficient is what we are doing here. And have a look at why that gives you a matrix, which is, in this case, 6 by 6, because we have 6 columns that were used for calculating, and we plot column against column, each column against every column in that data frame. So it's 6 by 6 matrix. And we remember from the plot, a column against itself, age against age, or height against height, and so on, is trivial. They're identical, so there's nothing really to detect there. The correlation coefficient is defined such that this value is 1 plus 1. If it was negatively correlated, if it was minus itself, it would be minus 1. So the whole range of that number that you can have here is from -1 to +1. So that makes ones on the diagonal, which are sort of trivial, something that you don't want to see. It's clear from the beginning, you don't need to look at it. And the numbers, yeah, some small numbers like 0.06. So age does not seem to be anyhow correlated with smoking habits, but you remember smoking was not really a number, it was just a yes or no. So maybe discard that, find a number outside age and systolic blood pressure, very weakly correlated diastolic blood pressure, even less. It's sort of trivial, right? So there's no really any proper correlation according to those numbers given here. And bigger numbers, yeah, there's something with 7, smoker versus systolic. And if we exclude the smoker as being strange because of binary, maybe here's something, height against weight 0.69 would be the largest number outside of that, the ones that includes this categorical variable. So there's something that would point to probably to a higher value. That's what we saw before. So there's a trend of height to be correlated with weight, which results in a coefficient larger than 0.5 in this case. Last feature, symmetry. Of course, comparing height against weight is the same as comparing weight against height. So the matrix is perfectly symmetric across the diagonal. Every value above the diagonal has its corresponding value below the diagonal. Now, this is sort of the quick fix. The way we use it, and the way it's typically used in machine learning, you remember, is not using the pandas data frame, but actually go forward and use NumPy arrays. So let's do that. Let's do the same thing. Let's get the same numbers from calculation on NumPy arrays. So let's first convert this to a NumPy array, the data frame as NumPy values. Very easy to get. I think we even, maybe I did that at some point too. You can convert the data frame into whatever you like, whatever data type you like. You can convert it to NumPy, open close parentheses, and you have that same set of numbers. You can just check its shape. That's the same as before. Check its shape, and we have 100,7 numbers now presented as a NumPy array. So on this NumPy array, we can now start to calculate the correlation coefficient. And I'll show you briefly how it does. There's a few small subtleties that you need to know. So first of all, we need to import the function from NumPy. So from NumPy import, and the function is called corcoef. There are more ways, but corcoef is one of those that you can just throw on it. And then we can do what pandas did when it excluded sort of that smoker thing at the end. What we can do is we can say columns is 5. We only want the first 5 columns. You remember, you don't use 5 in the actual code. You specify a variable such that if you want to use different number of columns, there's only one place to change it. So an important thing is this about, when you remember, there was integers and there was floating point numbers for the calculation of the correlation coefficient, we need them all to be, all entries need to be of the same time. So what we do is we do that data frame NP, and we make it all floating point numbers. So it just looks complicated, but it isn't. It's just a conversion. So we take whatever values we want to have and we convert them to floating point. So what do we want to have in square brackets? All rows. And then we want to have cols, the first 5 columns. No, we want everything up to col. So from 0, 1, 2, 3, 4 up to 5, you know, it's exclusive with the 5. So 0, 1, 2, 3, 4, that's 5 columns. So these are the data that we want, all rows. And to make sure we get them all the same, we use as_type. So as_type is a function that converts everything to, and then you specify what you want, integer, Boolean, whatever you like, we say float. Then you have the NumPy array, everything in floating point number, and then you can use the core coefficient, core coef, and you apply it, just copy that variable down to here to this variable, and then you get the correlation coefficient. One small thing, and then we are ready. And that is an argument. The core coef function by default checks along the rows. So it calculates correlations along rows, but actually we want to have correlation along columns, right? Every column compared to each other column. So we need to say that, and the argument is row var, so row variation or row, whatever that is. And we just set that to false because by default it's set to true. So it looks at rows, but if we want to have columns, we set that equal to false. And then we have it, and then we can have the data frame correlations. And the variable, we call it dfcor. And if we just say we want to see that result, you can see just this, 2, 3 small things that we have attended, and we have the same set of numbers that we had before above from core in pandas data frames. Why would we do one or not the other? It doesn't really matter. You can do one if you feel it's more comfortable with pandas data frames, you do that. I prefer NumPy arrays because I do everything in NumPy arrays. And you can see also some of the features that you don't know above here, you are made aware. Like, do you want to use rows or columns is of course a decision that you take. And if you use the default, it's somebody else took the decision. So sometimes it's good to do that explicitly. So here's our correlation matrix and our array called dfcor. And of course, outcome of an operation here is another NumPy array. So what I don't want to do now is something that you will find in the materials. These numbers, of course, you can now go forward and analyze them. It's not very much to analyze if you have 5 columns that we have used, but if you have 100 or 1,000 columns, it's well worth analyzing them, taking all correlation coefficients, making a histogram, calculating the mean of the correlation coefficients and the mean of the means and so on. Anything that you want to have, anything that you find informative, you can do that. What we want to do is we want to look at it. We want to have this overview. And because the numbers here, 0.091356 is not very intuitive to interpret, we try to make a graphical representation that is informative. So we use graphical, that means we make a plot equal subplots, and then we put something on the axis. Now, one way, it's an array, it's a 5 by 5 array, so that's a matrix, if you like, in mathematical speak. And the way to show a matrix is a heat map, right? You know, heat maps like color codes for the value that you have in every position. So it's sort of this a way of putting information from X and Y and Z coordinates into a graphical view. And the way to do that, you can use ImShow and many different types of plots like heat maps there, but you can use ImShow, which is actually one that we are going to look at when we do imaging. So image show, that's short for image show. And we want to see our correlation matrix. And let's just do it as it is. And of course, not to forget that semicolon at the end. We don't need to see that output. And yeah, if you wonder, yes, there are also ways to put the names of the columns on instead of the 0, 1, 2, 3, 4. Ask me on the forum if you need it, but let's just stay with this graph. We can see it's only 5 columns. It's easy to see. What do we see? So maybe the first thing is we need to have a sort of an interpretation of the values of the colors. And so we need a color bar. We need to see what each color means. So the way to find out or to get a color bar into the picture is to call that image object, give it a name. We can call it im. No, not im. Where is it? Here. The one where I create the heat map, give it a variable name, call it im or image. And then say, in that figure, put a color bar. And as an argument on that image, right? We could have multiple axes, but here we have created that image, put a color bar on that image and use a semicolon at the end to not see. And quite nicely, we can see, the dark blue is low values near 0, and the yellow is high values near 1. Just another twist. So of course, if you do this, you can see what's wrong. What is wrong is here, and we had that before, is this yellow stands out, it springs, it jumps into the eyes visually, but it's not what we want because it's diagonal, it's trivial. If you want to trivialize the diagonal, so to speak, there's a nice NumPy function. You can import it from NumPy import. And it's called fill diagonal. Fill diagonal is a function that helps you if we just apply directly to our data set, which is df core, right? The correlation from that data frame. And what we can do is we can replace the diagonal as is with any value that we want to have. So a good trick for correlation matrices, which are between -1 and 1, is to put the diagonal equal to 0. Because if we then use that same code, I just copy and paste the code from here and repeat that. And with the diagonal sort of put to 0, you can see now standing out is the strongest correlation rather than the diagonal. And this is the one between height and weight. It's in yellow here. So that's the strongest one. Everything that's sort of dark bluish, probably also you can interpret now means nothing, is not significant. It fluctuates around 0, but it's around 0 or 0.1. It's very small. And the second strongest correlation is between columns 3 and 4, the last but one and last. And that was it between the two blood pressure values, the upper and the lower blood pressure. So there's also some correlation, although not as strong as the one between height and weight. Okay, so that's nice. What else can we do? One more thing, if you don't like the colors here, I don't know if I showed that. Maybe I didn't really show that, but if you want to change the color map, the way to do it is to use the keyword argument CMap. And CMap, one of the color maps that is actually very good in a situation like this one, where we have sort of negative correlation, positive correlation, and nothing in between, is one that has one color on the one extreme, another color on the other extreme, and nothing in between. And one of the color maps that has this feature is BWR, which is white and red, blue, white, and red. And if you do this, you have, in this case, white around 0.35. You can also adjust it to have the white exactly at 0, so to make 0 disappear. And the way to do it, you define the minimum and the maximum value that you think are the extremes that you would like to see. The minimum in the correlation matrix is -1. So phi min, V, the letter V min, is the minimum of the color value in that map. And V max, you can put it to 1 because that's the maximum correlation. That's when they are identical. And if you repeat that, you get actually a very nice picture, which is now our summary plot. Maybe I leave the code so you can see it. Summary plot for those 5 columns that we have selected. All pairwise relationships as expressed by the Pearson correlation coefficients are visualized in this one plot. White meaning nothing really, that's 0 correlation or very weak correlation if it's lightly colored. And then strong red would be strong correlation. The stronger the red, the more correlations there are. The absence of blue means there are no negative correlations, no anti-correlations. And you can see those correlations that are stronger stand out visually. The others are sort of pinkish or somewhere between red and white, which you can forget. And such very good summary statistics or summary visual impression, but in this case, multivariate. Every column compared to every other column. Okay, that concludes our 2-part introduction to data frames. You know how to import, you know how to get univariate features, display univariate features. Now you've seen bivariate plots and quantifications of features. So we have a full overview because there isn't anything else. There's only uni and multivariate data features. If you do it for the whole data frame, you know everything about the data as an overview that you need to know, and which means we are ready to go forward. Before we go into the actual machine learning, we have 2 more specific data sets that require a bit of a specific way of analyzing things. And we'll do next time the imaging, images that have spatial coordinates as an interpretation. And after that, time series, which have a temporal order, which is something which we don't have in these things. They require a few special things, but it's basically what we have done here. To get an overview and to handle them just needs to understand what data are and what functionality is there. That's it. Thank you very much for watching, and see you in 2 weeks' time on this channel.
Thank you very much.